Hello everyone from Math 2200, Discrete Mathematics. It's Professor Wenson here again with a video on your Zybooks section 10.5. It's titled Counting Subsets, or might also be called Counting Combinations. Right. In the section 10.4 you counted permutations, where order mattered, position mattered. When you count subsets, or combinations, the order that things come in doesn't matter. Position doesn't matter. Alright, so let's take a look. So they're starting with an example. Consider a class with 20 students who must elect 3 representatives to the student council. The teacher conducts a vote and reveals the names of the 3 students who receive the most votes. He does not reveal how many votes each student received, or which one received more votes than the other 2. How many ways are there to select the 3 representatives? So this is a case where the position, the order that these 3 students come in doesn't matter, right? If Bob, Jill, and Jane are the 3 top vote getters, but they're not saying who got more votes than whom, you could have Bob, then Jill, then Jane, or Jill, Jane, Bob, Jill, Bob, Jane. Doesn't matter. It's Bob, Jill, and Jane are the 3 top vote getters. It doesn't matter what order they come in. So here the outcome of the election is a set of 3 students. Not a sequence. Right? It's a set, not a sequence. In sets, order doesn't matter. In a sequence, order does matter. And again, it's a set because there is no particular order imposed on the 3 representatives. The outcome, and notice they got the set brackets instead of parentheses. Remember, for a sequence, they're using parentheses. But for a set, they're using those set braces. And the braces will imply that order doesn't matter. Parentheses imply that order does matter. So please be aware of the difference. So this outcome of the set with Josh, Karen, and Ingrid is the same outcome as the set with Karen, Ingrid, and Josh, right? As long as they're the 3 top vote getters, it doesn't matter what order they come in. So a subset of size R is called an R subset. In counting the number of ways to elect 3 representatives, we are counting the number of different 3 subsets of students from a class of size 20 we can pull. An R subset, as I mentioned at the top of the video, is sometimes referred to as an R combination. The counting rules for sequences and subsets are commonly referred to as permutations and combinations, right? Permutations, you're talking about sequences with the parentheses. Order matters. Combinations, you're talking about sets with the braces. Order does not matter. Right. The term combination in the context of counting is just another word for subset. Alright, so there are examples here, right? And I'll actually write this out on paper. They're giving us a set. S is a set of elements with the set with elements A, B, and C. Now the first one, they say, if I gave you this look here, see the parentheses mean that this is a sequence. That means that this is a sequence, meaning that order matters. So this is totally different than A comma B. Right. Meaning that order matters, meaning it's a permutation. Right, you're talking about permutations. Right, and in this case, this would be called a 2 permutation because it's a sequence of two objects. As opposed to this, right, versus this, if I said, hey, this set with B and A in it, notice there are these braces. Right? It's a set. And in fact, this is a subset of set S. You see the braces, this is a set. And if you're seeing a set, that means that they're talking about order not mattering. Right? Order doesn't matter. And if that's the case, that's when you're talking about combinations or subsets. So this would be called a 2 subset, right? A subset of size 2 of set S, or a 2 combination of elements from set S. Again, the big difference is the order, right? Because this sequence BA would not be the same as this sequence with A then B. Even though the same two elements are represented, they're in the incorrect order. But when you're talking sets, this set with B then A like this is the same as the set with A then B. These are the exact same set, so they are equal, whereas if you change the order in a sequence, they're not the same, they're not equal. All right. Huge difference. Please, pay attention to the symbols. So yeah, this one with the parentheses would be a 2 permutation. This one with the braces would be a 2 subset or a 2 combination. All right. Now the question is, how many different 2 permutations from S are there? So let's go back. So what I'm going to do, I'm going to put over here the number of 2 permutations from this set. So I could have the permutation. Now I know it's going to be 3 times 2. There's going to be 6. Right? We talked about counting permutations in a previous section. But the reason I'm going to be drawing this in a second, you'll see I'm going to have 2 permutations on one side, 2 combinations or 2 subsets on the other side, and we'll create a function between them to help you in the future. All right, we'll see. I'll set up a little formula. Well, I'll motivate the development of a formula for the number of 2 subsets, or the number of R combinations. All right, so I could have A then B, or B then A, right? Again, these are sequences, 2 permutations, order matters. So those are 2, A then C, C then A, 2 more there, B then C, C then B, B, not D, I don't know why I wrote D, sorry, C then B. Okay, so there are 6 2 permutations from set S. And remember what this was. This was basically, this is P. I had 3 objects, and I was creating 2 permutations. All right, remember that this notation from the last section, or on your calculator, you saw this as 3P2, like that. All right. Now on the other side, I'm going to put 2 combinations or 2 subsets. So there's the subset with elements A and B. Again, this is the same as the subset with elements B and A, so I'm not going to write it again. There's the subset with elements A and C, which is the same as the subset with elements C and A, so I'm not going to write it again. And then there's the subset with elements B and C, which again is the same as the subset with elements C and B, so I'm not going to write that twice. And that's it. there are only two subsets from S. Now, as I was saying before, the reason I put these like this is, imagine we have a function. I'm going to create a function between these. And the rule for the function is this. It's going to be a function where the domain is the permutations, and the target set, the codomain, is the subsets. And the rule for the function will be this: whatever elements are in the permutation, that permutation will map to the subset with those same elements. Okay, so we have this would map to this, and this one with BA would also map to this. And then the ones with A and C and A, both of those would map to the subset with A and C. And then the sequences, the permutations with B and C and B, those would map to the subset with B and C. And what we have here is a 2-to-1 function. All right, this is a 2-to-1 function, because every output is mapped to by two inputs. Right. And remember, if it's a 2-to-1 function, that means the size of the domain is 2 times the size of the target. So that means that the number of two permutations is equal to 2 times the number of two subsets. All right. Now the number of two permutations we saw was 6 equals 2 times the number of two subsets. So clearly the number of two subsets must be 3. This must be 3 then, because 2 times 3 is 6. Right. Or you could say the number of two subsets was 6 divided by 2. Right. Again, the motivation here is for a formula. The number of two subsets is 6 divided by 2, which, this 6 was P32, the number of two permutations taken from those three objects, divided by, and then I'm going to write 2 as 2 factorial, and you'll see why. 2 factorial is equal to 2, because, for every two elements, there are 2 factorial ways of rearranging them. So you see the 2 factorial ways of rearranging A and B, the 2 factorial ways of rearranging A and C, the 2 factorial ways of rearranging B and C. So that's why I'm writing this divided by 2 as 2 factorial. Again, there's a reason for this, which will come up when we get to a formula for the number of R subsets, or the number of R combinations. Right. So how many two permutations? 6. How many different two subsets? 3. Right. Again, these ones were easy to list off. Later they won't be, right? They'll be larger sizes, larger sets, right? So this is what I was getting at, right? The function I just showed you was a 2-to-1 function. Well, we can create a k-to-1 function, a so many to 1 function, from permutations to combinations, or from permutations to subsets. So let me do this example here. So consider a small example in which subsets, a subset of 3 colors is selected from the set blue, green, orange, pink, and red. All right, so we're pulling out. All right, so I'm going to do the same thing. I'm going to draw another picture where we're going to look at 3 permutations and then 3 combinations, all right, or 3 subsets from. And I'm just going to use B, G, O, P, and R for the color. And I'm not going to write out those color words all the time. All right. So our set S this time All right, this set of colors, or I'll just call it set C. I'll call it set S. So this set of colors, all right, you have blue, so I'll use B for blue, green, G, orange, pink, and red. All right. So you have this set of 5 colors. And what I'm going to do is over here, the domain of this function is going to be the 3 permutations, right? They said we're going to take 3 of these colors. So I'm going to write out the 3 permutations. All right. So I'm going to start this and then I'm going to kind of pause it and come back when I'm all finished, because 5p3 is quite a bit. All right. So 3 permutations. So one of these, I could have the blue, then the green, then the orange. All right. And then I could do how many different how many different sequences will there be with these 3? Remember, there'll be 3 factorial. There are 3 factorial ways of rearranging these. So I could have this other sequence: B, then O, then G, then G, B, O, G, O, B, O, B, G, O, G, B. Okay. So all 6 of those have, B, G, and O. And those are all different 3 permutations. And in fact, I'm not going to write all of them because I think there's 120. Okay. So yeah, I'm not going to write all these, but no, there's not 120. There's only 60. But still, there's 60 of these. I'm not going to write all 60. Okay. Then the next one, another one I could have would be B, then G, then P. And, there are 6 ways of rearranging these. BGP, BPG, GBP, GPB, and then PBG, PGB. Right? 6 ways of rearranging B, G, and P. And again, I'm just breaking these up into groups of 6. Now, and so on. Now, the number of 3 permutations. All right. So I'll call the domain here, D for domain. The size of the domain is 5p3, right? 5p3, or that p with 5, 3, right? Which again was 5 times 4 times 3. That would be 60. There'd be 60 elements in the domain. Now, for the target set, right? For the target set with all the outputs, I'm going to have the target set be the 3 subsets, right, or the 3 combinations. So there's little braces here. So I could have B, G, O. And again, it doesn't matter how I rearrange them, these 3, as long as there's B, G, and O in it, it's this subset. And then I could have B, G, P. And more, right? And more. And it's going to be the same function. Now, the size of the target, right, the cardinality of the target here, is the number of 3 subsets, right? The number of 3 subsets taken from S. And there'll be a notation like with the P's for this. I'll write that up in a minute. All right, so I'm going to set up a function, but this time it's a 6-to-1 function, right, instead of a 2-to-1. See how BGO would map to BGO. this BOG would map to BGO. Or again, if a permutation has objects, it's going to map to the subset with those same objects. GBO would map to BGO, GOB would map to BGO, OBG would map to BGO, and OGB would map to BGO. And the same thing here, BGP, BGP. All 6 of these would map to this one subset. And so on. I would do this for all 60 of the permutations. But what we have here is a 6 to 1 function. A 6 to 1 function. And if it's a 6 to 1 function, that means that the size of the domain is 6 times the size of the target. Or, if you just divide by 6, the size of the target is the size of the domain divided by 6. Alright, and 6 is 3 factorial, right? The number of different ways to rearrange these sequences of 3 objects. So I'll say the size of the domain, divided by 3 factorial. Alright. So the size of the target, the number of 3 subsets is the size of the domain, which was that P with 5, 3, the number of 3 permutations taken from 5 objects, divided by 3 factorial. And this is what's going to be happening in general, right? In general, the number of R combinations or R subsets, which is going to be denoted this way with the C and then N comma R, right? You're going to have a set of N objects and you're going to take R subsets, R combinations, you're going to pull out, choose R objects. Or you might see this with the NCR, you're going to see this symbol on your calculator. Or you might see this, just a big set of parentheses with N on top, R on bottom. All these mean the same thing. These are all representing the number of R combinations taken from N objects. And this is going to be equal to the number of permutations. The number of permutations is the number of R permutations divided by R factorial. Right, just like you saw here, the number of 3 subsets is the number of 3 permutations divided by 3 factorial. And I had that on the previous page. The number of 2 subsets on my previous page was the number of 2 permutations divided by 2 factorial. That is just the general rule to count the number of subsets. Now we could also mess with this a bit. Remember this, there was a formula for the permutations that was N factorial divided by the quantity N minus R factorial. But now you also have this other R factorial in the denominator. So you have times another R factorial in the denominator. So here's another way to write the number of R combinations, or the number of R subsets. All right, so I'm going to put this in a nice box. Here, this is a... Okay. All right. So, getting back to the assignment here. So they say that P5, again, the number of 3 subsets would be the number of 3 permutations divided by 3 factorial. So that's 60 divided by 6, 10. Right? Or you write the formula the other way I had it, with the N factorial divided by, N minus R factorial. Right, 5 minus 3 is a 2 factorial, and then times R factorial, 3 factorial in the denominator there. So that's 120 divided by, and then 6 times 2 is 12, 120 divided by 12 is 10. So however you look at it, you've got 10 different combinations, 10 different 3 subsets. And they show you a kind of picture like that, like I did there, but they only do one of them. Alright, and they just show you in general, right, this development of the formula that I showed you. right here. They got r factorial first and then n minus r factorial second in the denominator. It doesn't matter. All right. Okay, so let's look at this example here. So consider a function that maps 5 permutations from a set 1 through 20 to 5 subsets from that set as well. The function takes a 5 permutation and removes the ordering on the elements. So how many 5 permutations map to the subset 2, 5? Basically, what kind of a function is it? When I was doing 3 subsets, it was a 3 factorial to 1, a 6 to 1 function. 6 inputs went to the same output. When it was a 2 subset, it was a 2 to 1 function, 2 factorial to 1. If we're looking at 5 permutations in 5 subsets, this is going to be a 5 factorial to 1 function. Now 5 factorial is 5 times 4 times 3 times 2 times 1. That's 120. 120 different inputs would go to this same output, would go to this set here. And again, there's the formula again. They say n choose r. I say it a lot too. When you talk about picking, how many subsets can you create from a set of objects? So if I have n objects and I'm creating a subset of r objects, that's like choosing them, just choosing r objects out of the n objects. So they call it n choose r sometimes, and I'll say that a lot. And then for permutations, I'll say n pick r. Right? Pick for p permutations. Choose starts with c combinations. So is combinations. All right. So what would be the value of 7 choose 3? All right. So I'll go to some paper here, and I'll show you a couple of these. All right. So this is if I have 7 different, 7 different looking objects. All right. If I have 7 objects, different looking objects, and I choose 3 of them, how many ways can that be done? So again, remember this is the number of permutations, 7p3 divided by 3 factorial. Now 7p3, that's 7 times 6 times 5, divided by 3 factorial is 3 times 2 times 1, that's 6, and then the 6's cancel, you have 7 times 5, 35. So if you have a set with 7 objects, and you're asked how many ways can I choose 3 of them, make 3 subsets, there'd be 35 different ways to do that. Now, let me show you again on the calculator where this is at. It's right underneath permutations. Right. No, this is from the last video. Right underneath permutations, right, if you hit the math button and go over to the PRB menu, you see number 3 down there is NCR. Right? Remember, there's NPR for permutations. That's when you're creating sequences with the parentheses and order matters. Pardon me. NCR is when you're creating the subsets with the braces and order doesn't matter. And choose R. Alright, so before you enter that though, on the older ones you got to enter a number. On some of the newer ones you can just go enter NCR and it'll have you fill in the N and fill in the R and then go through the calculation. But here I have 7 objects, and I go to the NCR and I'm choosing 3 of them, and how many ways can that be done? 35. Right, as I had here. Alright, the next one is what 7 choose 4. So again, this is the number of permutations, 7p4 divided by 4 factorial. So this is 7 times 6 times 5 times 4. Remember, you start with 7 and just keep multiplying by 1 lower until you get 4 factors. Divided by, now 4 factorial is 4 times 3 times 2, times 1, but there's really no need to write times 1. Let me do some canceling. 3 times 2 is 6, so 6 is cancel. There's a 4 there, and again I'm left with 7 times 5, 35. Alright, and here's something, now they're not always going to be 35, right? But let me show you a nice property. N choose R will be equal to N choose N minus R. All right. So basically, as long as the two lower numbers add up to N, they'll be equal. All right. So let me show you on the calculator. I have 7 objects. Choose the NCR 4 objects, and I'm creating 4 subsets, 35. Let me show you another example of this rule working out. So another example of this, if I had 8 choose 3, that would be equal to 8 choose 5. And again, as long as the two numbers here add up to the top number, right? They add up to 8. And you can check this out on, I'll just do it on the calculator. 8 choose 3 is 56. And you see that 8 choose 5 will also be 56. Okay. So this is a nice rule to kind of cut out some work sometimes. All right. So again, those are both 35. Now 100 choose 1 would be 100. And I'll let you figure that out. 100 choose 100 would be 1. Right? Remember, 0 factorial is 1, if you ever come across that. Alright, now here they get to that rule I just showed you. N choose R is equivalent to N choose N minus R. Alright, for the following questions, express your answer as N choose R. So here you're actually asked to write out the word choose. So here a teacher must select 4 members of the math club to participate in an upcoming competition. How many ways are there for her to make her selection if the club has 12 members? Well, that would, again, order doesn't really matter. You just say, hey, you 4, you're going. Right? It doesn't matter what order they come in. So this is just 12 choose 4, right? You just type in the word, they want you to type out the word choose. But also 12 choose 8, right, from that rule I showed you a second ago. Because you could choose 4 people to go to the competition, or you could say that you're choosing 8 people not to go to the competition. Same thing. And I'll leave this one here for you. Alright. Next, part of this section is we're counting binary strings with a fixed number of ones. And this will be a combination problem. You're choosing things, choosing positions. So the idea is used to count subsets of a particular size. Can also be used to count binary strings with a particular number of ones. So the animation below shows how to count the number of 5-bit strings that have exactly 2 ones by showing a bijection between the strings to be counted and the number of 2 subsets. Okay. So look, if you have the set with 5 elements, 1, 2, 3, 4, 5. See these 2 subsets, 1, 2. Well, if you're creating bit strings, if the element's in the set, you just put a 1 there, and if an element's not in the set, you represent it by a 0 and create these bit strings of length 5. So you got 1, 2, right? So that would be 1, 1, and then 0, 0, 0, and then you see 1, 3. That subset has 1, 0, 1, 0, 0. Another one. Every single subset, every single 2 subset can be represented as a bit string of length 5. And again, the number of 2 subsets is simply 5 choose 2 then, right? Which would be 10, as you can see here. And I'll let you play with this animation. And counting paths on a grid. I'll let you read that example. All right. So let's say here, define a bijection between 5 subsets of the set 1 through 8 and 8 bit strings with exactly 5 ones. A subset X of S with 5 elements maps onto a string X so that J belongs to X if and only if the jth bit of X is 1. So what is the string that corresponds to this set? So again, 1's in there, so I put 1 in the first position. 2's not in there, so I put a 0 in the second position. 3's in there, so I put 1 in the third position. 4 is in there, 5 is in there. 6 and 7 are not, and 8 is, right? So the bit string that would correspond to that subset be 1 0 1 1 1 0 0 1. Then how many 8-bit strings have exactly 5 1's? Again, that would just be 8, choose 5. Right? You have these 8 positions to fill, and you just choose which 5 to go, put a 1 in. And it doesn't matter what order you pick those positions in. No matter what order you put them in, you're going to put 1's there. So this is a combination problem, a choosing problem, a subset problem. So this will just be 8, choose 5. And now the 8 choose 5 or 8 choose 3. Right? You could choose where the 5 1's go, or equivalently, choose where the 3 0's go. Same result. All right, and I'll leave the last one to you. All right, and then the challenge activity. Again, they're having you write combinations or subsets with the C and the NK, kind of like when you had permutations, they wanted the P typed. And use the caret button above the number 6 on the keypad. Use that for powers. Alright, so here a bit string contains 1's and 0's. Right? How many different bit strings can be constructed given the following restrictions? Now, if the length is just if it's just the length is 21, that's not really restrictive. So for each of those 21 positions, I can have a 1 or a 0. So for each of those 21 positions, there are 2 choices. And applying the product rule, there's 2 times 2 times 2 times 2 times 2, to 21 times. That would be 2 to the 21th power. All right, 2 to the 21st power. That's a big number. That's how many bit strings of length 21 there would be. Now, if the length is 27, and it has to start with 1 0 1, well, that means the first 3 positions are already filled. You don't have to worry about them. 1 0 1 are already picked. And then you have the remaining 24 positions to fill, and they can be anything. They can be either 0 or 1. So for the remaining 24 positions, you have 2 choices each. Applying the product rule, there would be 2 to the 24th power number of strings of length 27 that start with 1 0 1. Again, a pretty big number down here. Right here, length is 28, and it has exactly 5 zeros. So this is a combination thing. This is, I have 28 positions to fill. I choose 5 of those positions to put a 0 in, and then in the other 23, there'd be 1's. So you could have 28 choose 5, to pick where the 0's go, or you could say 28 choose 23 to pick where the 1's go. But I'll just write it as 28 choose 5. So you got C, and then again you have 28, comma, 5. It's 28 positions, and I'm choosing 5 of those positions to place a 0, and then the other 23 would have to be 1. All right, and I'll leave these last 2 to you to play around with. So not so bad. All right, so pay attention to this part. It has exactly 3 1's in the first half, so in the first 12. So you got that number of choices, and then you're going to apply the product rule times, and then do it for the second half as well. All right, so hopefully that wasn't so bad looking at and watching me do. You got your additional exercises. Some of these are assigned, some are not. I would still recommend looking at all of them just to get more practice, more exposure to the material. And of course, if you have any troubles, maybe look at the solutions after, but only after working on it for a bit. Try to work on them first. Try to get figure it out on your own before you look at the solutions. And if you have any questions, send them my way. Send me a message and I'll get back to you as soon as possible. And thank you very much for watching.